So we will continue with our next example, and we will have a shunt stage now. So the schematic of our shunt stage is here. We are going to follow a very similar procedure as we did before. So we start doing a hand calculation using the asymptotic model. So we have that for our asymptotic model, this this circuit looks like this. Then we have here at capacitive zeta L. There is a capacitor zeta L here. Just change it to a capacitor here, CL. And then we have a feedback resistor here, a series resistor here, and IS. Okay, and this is connected here. So we see, assuming that we have a null order, that all the current flows directly to the output through resistor RF, and the output voltage will be equal to minus IS times RF, and the transimpedance will be equal to minus RF. So this, in this particular case, as we saw before, this is 1 mega ohm. So we have a 1 mega ohm impedance, and the source is 100 kilo. Okay, so and then we will have our asymptotic gain, assuming a null implementation, will provide 1 mega ohm transimpedance. Now we need to calculate the A beta null. We need to calculate the low frequency loop gain, and so then let's first draw the model for that. So that will be RS CGS. Here we have CGD. There will be the feedback resistor in parallel here, RF. And then we replace the transconductor with a test current source, IT. And then we have RDS and the output capacitor here, CL. Then we can put here a reference. Okay, so now we just follow this current, and this current for DC or low frequencies will flow like this, and create a voltage drop over resistor RS. Our target is to find VGS here. Okay, so we have the current divider, and this current divider will be equal to IT times RDS divided by RDS plus RS plus RF. So that will be this current that flows in this branch. If I multiply this current by RS, then I will get the voltage drop. It is a minus because it goes in the different direction that plus minus in BGS. So that will be our BGS, and our beta will be equal to BGS divided by IT, and that will be equal to minus RDS times RS divided by RDS plus RS plus RF. and at low frequencies we will have that this is going to be equal to minus Gm time RDS RS divided by RDS plus RS plus RF. Okay, and then when we replace all the values, what we get it is minus 21.7, and then we calculate the closed loop gain. That will be like this. This is plus here, and I will have as a result that I will get minus 955 kilo ohms. Okay, so let's take a look very quickly what the simulator tell me to the simulation, and then I have for the asymptotic gain. The asymptotic gain, it tell me 1 mega ohm at low frequency, so that is what I calculated. And for the closed loop gain, it is giving me around 952 kilo ohms. Okay, very close to what I calculated. The loop gain, it is giving me 21.7. Let's see how much did I calculate it here. It's 21.7. So yeah, basically it is the same as I calculated with my hand calculation, so it's correct. So we can go forward and calculate the position of the poles. Okay, so and we are going to do the same as we did before. We merge CGS, all the gate to source and gate bulk capacitance. In CDS we merge CDS and CD bulk and the load capacitance, so we merge totally there. And then we're going to do the calculations for the input and output poles. Let's start with the input pole. So our model for that calculation will be like this. So we have CGS, and then we have that is in parallel to RS. Then we have RF. Then we have only RDS here. So the equivalent resistance for pole number 1 will be equal to RS in parallel to RF plus RDS. Now let's do the same for CGD. So we have RS here, RF, and then we have just can put it here. No, that's okay. Let's put it here. CDS, and that will be RDS. So the equivalent resistance for the pole 2 will be RDS in parallel to RS plus RF, and then we can calculate the position of the pole number 1 equal to 1 divided by CGS. Will be CGS 1 divided by R 2 CDS. Okay, so that will be my estimation for the pole position using the open time constants, and let's see how good or bad they are. Then when I calculate with using this first approximation, I got the position of the first pole in 5.85 megahertz, and this is pole 2 associated with CDS. Then it will be 676 kilohertz. So let's take a look when we simulate in cadence what it is the exact positions of these ones. So we get the position of the first pole. It is minus 5.8, so it is pretty close to what I calculated. The position of the second pole, it is a little bit different. It is telling me minus 458 kilohertz. So what we can do here, it is try to improve our model a little bit. So we are going to load CDS with CGT. So we introduce CGT, and then it goes down a little bit to 605 kilohertz, and yeah, then I can assume that it is not so bad now, that first-hand estimation using the open time constants. I can do a first estimation of the available bandwidth. We have the loop gain product, loop gain pole product here. It will give me around 9 megahertz. And then I check if I can use a phantom zero. So the sum of the both poles is 6.4 megahertz, and the square root of the available bandwidth is 12.7 megahertz. So it might be possible to add a pole in order to move the poles to bandwidth positions, so borderware positions. So we have a summary of the simulations, and then if you want to simulate it this stage, it is available as part of the course material. Let's see, it will be here as a shunt. So the setup follow exactly the same ideas that we had for the serial. So this is exactly the same thing. We use 4 tests. One for the closed loop gain, asymptotic gain, loop gain, and we do a rod locus. And the main idea is that now for the closed loop gain, we set the source to 1 and the test current to 0, and then we just calculate the transfer function B out here. And for the asymptotic gain, I keep the same template, but the same test, but I change the value of GM1 to large value 1 kilo Siemens, for instance, to emulate the infinite. And then I run the simulation and check the pole 0 and the gains. And for the loop gain, I will be setting this one to 0, IS to 0. I will enable the test current. I will put 1 for this one, and then I will be running the AC simulation and finding the gate to source gate voltage. No, the source is grounded. The gate voltage for all the frequencies of interest, and I will have to disable the transconductance GM1. This has to be equal to 0. So that only the only source that I have will be this independent current source. And I will check the pole 0 positions at VG. So we can take a look how this setup look for the loop gain. We look like this. The transconductance is equal to 0, and the pole 0 will only track as an output the gate voltage, and it will take the input source as current I4. And I will do the rod locus also exactly the same way as I did before, just swapping the transconductance. Okay, so you can test this one yourself. Here is the summary of this simulation. We find also that there is a there is a pole in the asymptotic gain, and that is this pole in the asymptotic gain, it is minus 6 megahertz. It will become 0. Okay, so it is minus 6 megahertz. It will become a 0 in the loop gain, and we can see at 6 megahertz we have a 0 here. We have a 0, so this pole become this pole in asymptotic gain become a 0, as we discussed before. Okay, so now we have the root locus also. We can run the simulation so I can show you. Okay, so we have here the root locus, and then we start sweeping the transconductance and checking how the position of the poles evolve from their original positions that we calculated from the loop gain towards the final position after the transconductance is final value of the transconductance is calculated. And then we see that there was a phantom 0. We cannot see the 0 here, it was somewhere here. We have phantom 0 here, and then the poles are being manipulated by this phantom 0. So they go around, they crash again in the origin, and then they split. One goes to higher frequencies, the other goes to lower frequencies. Okay, until they rest in these positions. Now, besides the basic stages and the local feedback stages that we have studied, there are another interesting stages that are worth to study, and one that we are going to use a lot in analog circuit design is the current mirror. So the current mirror is used for many applications. One, it is to do the biasing, as we're going to have a separate lecture, but we can also use for amplifying signals. So very quickly, in a current mirror we have one transistor that it is the reference transistor. It is diode connected. We call it this a diode connection, and then we have reference current here. Then we have the following connection. So both are sharing the same VGS, but they might have different dimensions. Let's suppose that it is they are different length and different width, but they share the same VGS. And the transistor on the left, it is always on saturation. Okay, in this particular case, VDS, it is going to be equal to VGS. In other words, VDS is also always going to be larger than VGS minus VT, so VTH. So this transistor is always on saturation. So the model for saturation applies for this transistor. And yeah, we can say that the relation of the current between these two transistors, we call this transistor 2, M2, and this transistor M1. And the current that flows here, it is going to be I2. Then we have that I2 divided by, and let's call this current I1 also equal to Iref. I1, that is going to be equal, and then they are in strong inversion, but the resultant is basically the same for weak inversion also, but they are in strong inversion, that then we have U and C ox divided by 2, 1, L1, and then that will be UGS minus UTH square, and then we will have the same for the other, C ox 2, L2, and S minus VTH square, and then we see that this disappears, this disappears. This is the same for both, because both share gate and source. So this disappear, and then we have that the current ratios between these two transistors depend on the geometry of the transistors, the width and the length. Now, for practical purposes, almost always we keep both lengths the same, so the transistors have the same length, and we can match these devices much better. So if both are the same, these disappear, so that will be equal to that will be 1 and 2, sorry. So that will be 1 and 2, 1 and 2. Okay, and that will be 1 and I2. So that will be the relationship between the currents. So if I have, let's say, here I have 1 milliamp, and this is has a width 1 L, and this has 2 times the width, the length, then I will have 2 milliamps here. So just changing the width of the transistor, I can change the amount of current that passes here, and this is for DC. Now let's see what happened in for signals in AC. For AC, we will have to put the small signal model, and for the small signal model, and I'm just going to draw it for low frequencies. For DC, we have, this is GM 1 BGS 1, this will be BGS 1. The gate, it is connected to the drain, so we have connected this gate and this drain, and that will go to the second transistor here. Okay, that will be like this, and in the second transistor we have the following. It will be GM2 BGS2, that it is this voltage, BGS2, and that is what it is going to be connected to the load here, RL. Okay, and then here we connect the current source. Here we connect the current source. Now we have already talked a little bit about this configuration of the diode connected transistor, and we have seen that in this configuration, this behaves like a resistance with a value 1 over GM. In this particular case, it will be 1 over GM1. 1 over GM1, so that will be the resistance. Is normally small resistance, which is good because when we connect a current, we want to have a small resistance sinking all the current. Think that we always have series resistance here. So if we assume that the 1 over Gm it is much smaller than the source resistance, then all the current is going to flow through the diode connected transistor, and it is going to produce voltage VGS2 equal to ES divided by GM1. Okay, so that is this current, it is going to be transformed in this voltage, and then the output current that I have here, E out will be equal to there will be GM2 times VGS2, and this will be GM2 times IS divided by GM1, that is E out, or E out divided by E in, the current gain, will be equal to GM2 divided by GM1. Okay, so that is very interesting result here for the small signal model. When I have some signal current entering here, if this is a signal current AC coming here, this current will be amplified here, and it will be amplified by the ratio GM2 divided by GM1. Now the currents are related by these ratios. If we have GM2 is going to be equal to I2 VGS minus VTH, and GM1 is seeing that we have GM2 divided by GM1 is equal to, it will be 1 VGS minus VTH. This is the same for both transistors, so this disappears, and then due to this relationship, this will be equal to the ratio of the widths of the transistor. So the same as for the biasing currents, the transconductance have the same ratio. So this will allow me to do some current amplification. So, okay, this is going to be the current amplification for the current mirror. I can do signal amplification in the current domain, which it is useful in many applications. Now, to have very large gains, I will have to have very large current transistor ratios, and sometimes it is not very practical. There are other aspects that are also interesting. We're going to talk about noise in the next lectures. They are very noisy, the current mirrors. And something else is that we take a look here. This transistor have connected the gate and the drain voltage together, so VDS and VGS is exactly the same. But in this one, no. The drain voltage can float, can take different values than in transistor 1, and that will change the current that passes through the transistor due to channel length modulation, a situation that it is more problematic in when the length is very small. Okay, but current mirrors are extremely useful. We are going to use them a lot. We are coming back to current mirrors later.